Today, you guys are going to be learning how to use your accelerometer in your cell phone to measure free fall. So today, you actually won't need your notebooks or even pencils. You're just going to need your cell phone, and we're going to use that in Spark for you to do some stuff. Also, you're going to find out that we're going to use that to measure acceleration of gravity on Earth, which is called little g. You remember, what is the acceleration of gravity on Earth? I'll give you a hint. It's the same for everything on Earth, and it's on your yellow paper. So here are skydivers falling before they use their parachutes. And my question for you is, do you think these guys are in free fall? They kind of look like they're in free fall. They're falling freely, but what we find out is as they fall, they go faster and faster and faster, but as they go faster and faster, the air, you can see the air blowing on them, the air affects them more and more. So let's talk about free fall and what actually happens. Skydivers will reach something called terminal velocity, their ending velocity, which means they start falling at a constant rate and they don't speed up anymore after a certain time. How does this work? So let's go back. Remember free fall? Free fall means there's no air resistance. The only force is the force of gravity. So let's say we had a feather falling and a ball falling. If they're in free fall, the only thing pulling the feather down is the feather's weight, and the only thing pulling the ball down is the ball's weight. And what happens is they both fall at the same acceleration, 9.8 meters per second squared, because even though the feather has less weight, it also has less inertia. So less inertia and less weight, so it falls at 9.8 meters per second squared. The ball has more weight, but it also has more inertia, so it falls still at 9.8 meters per second squared. Now, as they fall, they actually have air resistance on them. We'll keep this simple and assume that the air pushing up on the feather is about the same as the air pushing up on the ball, even though the ball is more aerodynamic. But let's just say it's about the same amount of force. And look at these pictures. What do you notice about the free body diagram of the feather and the free body diagram of the ball? Will the feather accelerate? So what we find out is, just by looking at our picture, the feather is in equilibrium pretty quickly. It's in equilibrium because the force of the air up and the force of gravity down become the same pretty quickly. As soon as the feather starts falling, the force of air up pushes up against it and balances out the weight. So the feather doesn't accelerate anymore. It just falls at a constant rate, assuming it's not going to flip and flop like this. The ball, on the other hand, looking at the ball, you can see that it's got an unbalanced force. The weight pulls more than the friction of the force of air up. So the ball keeps speeding up and speeding up. What do you think is going to happen as the ball speeds up? What's going to happen to the force of air pushing up on the ball as the ball goes faster and faster and faster? The force of air on the ball increases. It'll keep getting, as the ball goes faster and faster and faster, the force of air goes more and more up and up and up until something happens. Eventually, the force of the air up, the ball is going so fast, the force of air up equals the weight down, and it is an equilibrium. Okay, so at some point, both of the objects reach what's called terminal velocity. Terminal means the ending velocity. The feather reaches ending velocity and the ball reaches ending velocity, and they don't accelerate anymore. Notice though, the feather is going to reach its ending velocity much more quickly than the ball. The ball has to go faster and faster and faster. So the ball ends up falling faster than the feather, even though they're both in equilibrium and not accelerating. One example of something using air resistance like this is spiders. Spiders will shoot their web up into the air like this, and it'll actually let them sort of float or fly. This is a picture from Brazil of thousands and thousands of spiders using their webs to float and fly in the air to travel away from each other, so they're not all on one spot, and they can spread out and live without, eating all the same food. So they're using terminal velocity. And actually, they have so much air resistance they can fly upwards for a while into the air when the weather's right. Now, what I'd like you guys to do is get out your smartphone, go to your app store on your phone and download SparkVue. It's a free app. Notice how you spell it, Spark, V-U-E, like that. And the symbol looks like this blue square with some white dots on it, SparkVue. And so what we're going to do is have some fun with our phones using the SparkVue app. It's a similar app that you guys ran in my classroom, but it's going to work on your phone. Follow these instructions when you do this. You're going to start the app, okay? And when you start the app, you're going to get a screen like this. If you ever make a mistake and you want to go back, you can always go back and click on this 3 bars here to open up the menu and hit Start New Experiment. You don't have to do this the very first time, but if you mess up, you always just keep going back, start new experiment each time to reset. And you can also you never have to save a file. Okay, so if it ever asks you to save a file, just select No for save a file. So the first time you run it, it looks like this. Click on Sensor Data because you want to use the sensors on your phone. And then this screen opens up. And what you want to do once you open this up, first you click on this little toggle button here, which is Onboard Acceleration Sensor. Click on that. Then you're going to go through and fill in these 3 boxes, acceleration X, Y, and Z, and make sure this box is empty. And then you're going to click on digits, not these other things, click on digits. So go ahead and do that. All right, if you did it correctly, you should have a screen that looks like this, and it's showing your acceleration in the X, Y, and Z directions, and it's ready to record them. So what I want you to do is hit the start button, and you'll start being able to read the accelerations in the X, Y, and Z directions. First, after you hit start, I want you to lay your phone down flat like this with it facing up. Lay your phone flat and just leave it sit there. And what you notice is something like this. You'll have 3 different accelerations, but in the Z direction right here, the Z direction is in the same direction as the front of your phone. So it'll measure something around 9.8 meters per second squared, which is acceleration due to gravity. The reason it's negative is because negative is the negative direction is facing upwards on your phone, so it'll measure negative. Now what I want you to do is try to tilt your phone, keep it on the table, and tilt it up like this so that it's on the edge of the phone like this, and you'll notice something different. Now you'll see that instead of the Z direction being 9.8, it's the X direction. That's because the X direction is edges of the long edges of your phone up and down this way. So go ahead and try, there's acceleration gravity again. Go ahead and try tilting it slowly on different edges, and you'll notice all 3 numbers different ways. This is the short edge, this is the long edge, and this is the face of the phone. All right, so now you've got acceleration of 9.8 meters per second on different edges. My question for you is this. Is your phone actually accelerating right now? No, it's just sitting on a table. Why is it measuring acceleration? Well, let me show you kind of with this stuffed animal demonstration. So for this little dog stuffed animal, when I accelerate it forward, you can see its ears move, right? When I accelerate it backwards, right? The ear moves. You can feel that on your head and your neck. Now, if I just take the dog and face it upward, the ear moves back the same. It feels the gravity pulling down on it as if it's accelerating upwards, right? And the same thing happens if I face it downwards, right? When it faces downwards, the ear moves that way. It feels like it's accelerating this way, okay? So you can see that it feels like you're accelerating because of gravity, even though you're not accelerating. We actually use this on rides like this. I don't know if you've seen one of these rides at the arcade. It's like a roller coaster ride, and as it moves around, and the whole body of the ride tilts different directions to get that feeling that you're accelerating, even though you're not actually accelerating. You can also see this. There's a ride at Great America called Mass Effect New Earth, and I put a video on Google Classroom. You can watch this if you want. It shows They wear 3D glasses, and then their chairs rotate to have the feeling that they're accelerating, even though they're not actually accelerating. We're gonna try 2 more experiments. What I want you to do, click on the 3 bars, put Start New Experiment, okay? And then again, you don't have to save the file, so hit No if it asks you to save a file. You're gonna hit Sensor Data again, okay? And this time, you're going to not have these boxes on. You want acceleration. This box should be clicked on. You want the result, and this will add all 3 accelerations together into a vector, so it'll give you the resultant. It's called the resultant. Acceleration resultant, and then click on Graph. All right, now go ahead and put the phone flat on the table again, but this time you're going to get a graph. Then hit Start and get a graph, and after about 5 or 6 seconds, hit Stop. Okay, if you do this correctly, my question is, which of these 4 different graphs did you end up getting? A line straight up, a line at an angle this way, a line at an angle that way, or a line straight across? Which of these 4 graphs did you get when you recorded this? You should have got a graph that looks something like this. Now, it might not be perfectly flat, but it's fairly horizontal. And what I want you to notice is, right here, this reading here is 9.8 meters per second squared. It's measuring the gravity again. Okay, we're going to try one more experiment. This time, I'm going to have you guys carefully toss your phone up in the air and catch it again while it's recording. So make sure when you do this, you want to do this probably above a padded surface, like above a carpet or maybe above your bed. So in case you miss the phone and it falls, it'll land on something soft. So go ahead and set your phone up. Actually, you could just use this setup here and then just hit Start when you're ready, because it'll just record right over top of this and get a different graph. So let me show you how to do this with a helper. This is Mrs. Colby from Blaker Kindred Junior High. She's going to help me out demonstrating what to do with your phone. All right, so you have the phone set up, and then you're going to hit Start. It'll start recording, and then you're going to carefully toss it up in the air and then catch it again. All right, and then go ahead and hit Stop. Okay, and this is what you should have when you're done, something like this. All right, now that you're done, you should have a graph that looks something like this. Okay, so let's talk about the different parts of this graph. Again, this is measuring acceleration. So first, it's just below 10. This is when it's resting in your hand at the beginning. And this is when it's resting in your hand at the end. Beginning and ending, it's got acceleration. It measures, it feels like it's, gravity's pulling it down, so it measures that first. Okay? Then, what you get here, suddenly the acceleration goes way up. This is you tossing it upwards. It's measuring gravity pulling down, but then it's adding the extra acceleration of you pushing up. So it's measuring the force of gravity plus your acceleration of the phone as it's moving upwards. And then on this side here, this is going to be at the end when you catch it. You might have a bump like this up. This is the acceleration of the phone being accelerated upwards again when you catch it, along with the acceleration of gravity. Now the really interesting part is right here in the middle. Right here, you should have a point. If you did this correctly, there should be a point where the graph goes straight down and flat across at 0. 0 acceleration, right? For some point right here, you should see a dip down. 0 acceleration. Guess what? At that moment, that is called free fall. That's when your phone is in free fall for an instant up in the air, because the phone is actually falling at the same rate as gravity's accelerating it down. So it feels, well, we call this, it feels weightless. It feels like it has no weight. Free fall. So free fall is, now it's actually accelerating, but because of gravity pulling it down, the accelerometer inside the phone measures the downwards acceleration from the gravity pull, and then also the acceleration of the phone itself cancels it out. So it feels like it's not accelerating at all inside free fall. And that's it for today.